So now that we have talked about the way that Windows creates processes, let us look at the way Linux does that. Linux inherited the process API from Unix. Unix is a historical system. It actually influenced Linux a lot. We talked about Minix a bit last time, but Unix is also one of the forefathers of Linux. And you might want to read a bit about the history of Unix on Wikipedia if you do not know that history. And Unix, the Unix process API had a philosophy, and the philosophy was basically that you need a few functionalities in the operating system, and these functionalities include, they're not limited to, but they include being able to create a new process. So you want an operating system, be it Linux, Unix, BSD, any of these Unix variants, to be capable of starting a new process. Yeah, we sort of saw that in the create process for Windows, right? You want the Linux system or the operating system to be able to destroy a process. So you create a process, the process goes to basically do weird things, tries to access memory that it is not supposed to access, or any of these sorts of things. You should be able to destroy it. Maybe you want to destroy it because you're running out of resources. Okay. Of course, many processes will run and just exit by themselves when complete, but you need to be able to forcefully also kill them. You need to have a mechanism to wait. So sometimes the process is taking too long and you don't want to kill it now. You want, for example, if you're planning to restart the system, if you're waiting for results from that process and you do not want the program to proceed without getting these results, then you want a way to wait for the results. There are other miscellaneous controls. For example, you want to be able to suspend the process, basically stop the process temporarily because you got an interrupt. We talked about interrupts and what happens with interrupts a bit during the last lecture. You want to be able to resume the process because, well, you were waiting for input from memory. We talked about the memory architecture. You were waiting to basically fetch from the main memory into the L1 cache. You had a cache miss, basically, and you wanted to get memory from some memory lines into your L1 cache, so the process can block until you basically have this data in your L1 cache. And you want to be able to get status information about a process. So these include, for example, how long it has run, or what state is it in, and so on. So this is a high-level view of how process creation occurs in Linux systems. You have the code and the static data on disk. This is basically the program that you programmed. When you start the process, okay, the first thing that the operating system does is basically to load your code, the code of the program, the code of the process, and its static data into memory. And basically doing that, it creates an address. Before doing that, it needs to create an address space for the process. So if you start the process, what you're actually doing is that you create an address space in memory. So this nice dotted line, you load it, you load the process you load the code and the static data from disk, you create a heap, and you create a stack. Back in the days, it used to be that when you start a new process, you would load the whole application, everything about the program, into memory. This is very inefficient because in many cases, the applications are pretty large and they would actually take occupy the whole memory, for example, especially with today's applications. So right now, modern operating systems, what they do is that they lazily get the data from the storage device into the memory. And basically, as we gave an example last time, by a game that has multiple levels, you do not need to load in all levels of the game into your memory. You just need to load level 1, and then when you're approaching the end of level 1, you start loading level 2. I mean, this is an easy way to conceptually think of this. So as I just said, that part of creating the address space is actually creating the stack and creating the heap. The stack is used usually for storing local variables and function parameters and return values, while the heap is used to store dynamically allocated data. So, in short, the process creation passes through multiple phases. First, you're trying to initialize the process. Okay, so you're reading while you're reading it. And once you have everything in memory, you also need to, in Unix especially, you need each process to have 3 open file descriptors, basically 3 open places where the process can write data out of the box. Standard input, which basically is the way that the process reads your input from your keyboard, for example. Standard output, which is basically typically your screen unless you redirect that, and an error, where if the process runs into errors, it will throw the errors into this error file. So once you have done that, then the process is ready to run. Okay, and until now, the program has not started running. It has been initializing, basically. And here comes the main function that we program with. So historically, once you load your program, your process into memory, now it's no longer a program, it's a process. Once you load it into memory, the operating system searches for the main function, okay? And you jump to the main routine because this is where the process will start, and the operating system transfers control of the CPU to the newly created process. Now the process is running. So in a simplified view of a process, the process can have different states, okay? One of them is when you're still initializing, okay? So the process is blocked. You cannot run the process before you have memory and memory allocated and stack allocated, heap allocated, before you actually locate where the main function is. All of this must be done while the process is not running. So it's in a blocked state, okay? Once you have all of this, you are now ready to run, okay? So you go into a ready state. The process goes into a ready state. And then the operating system basically looks at what processes are now in the ready states and schedules one process at a time to get some CPU time, and then after some time deschedules it. We'll talk a lot about how this is done later. Okay, so when a process is running, it is occupying CPU actually and executing instructions, doing useful work. When a process is ready, then it has everything it needs to actually be running. It's not waiting for anything. When a process is blocked, it's basically waiting for something, and that thing can be, as I said, while you're initializing, or it can be basically that you're trying to read data from disk, or you're trying to read data from the user, etc. So if you trace process state, and if you're just looking at CPU, then you have here time, you have process 0 and process 1. Only one process can be running at a time if you have a single CPU, right? Because you need multiple CPUs. If you have multi-core systems, which most of us now have, then you will have different processes running in parallel. But just to simplify, let's think about the system as if it has a single core, a single CPU. So process 0 is running for four time units, and then it finishes. It's now done. Now process 1, since process 0 finished, process 1 now can run because the CPU is empty. So it starts running until it's done. This is a very simple view without interrupting the processes in any way. But if you have a process that, again, single CPU tries to run and reads data and run and reads data and so on, then the process can run, maybe process 0 will run for 3 time units, and process 1 during that period is ready. It has everything that it needs. It was initialized. But then process 0 needs to read some data from I/O. So it goes into a blocked state. While it is in the blocked state, now process 1 can run because the CPU is no longer needed. This process 0, will not run unless all its data is there, unless everything is ready for it. So while this is blocked, this one continues running. But now since process 1 started running, well, once you have all the data for process 0, you do not need to necessarily go back to process 0. You might do that, you might not do that. That is basically what the scheduler does. It decides what to do once you have the I/O data. So in this case, for example, the scheduler does not decide to change who runs now. So process 1 continues until it's done, while process 0 remains ready and then starts running again until it is done.